Ada lagi? Ada lagi. Okay. Okay. Right. Okay. Right. Okay. So just to recap. Okay. So shear design. We started off with this example. Okay. We start off with this example. So in this example, we have a span, we have a beam. We have a beam that spans 8 meters, right? So we have a beam that spans 8 meters. So basically what we have is we have a beam. We have a beam that spans 8 meters. It's carrying a UDL of 200 kilonewton per meter run. Okay. Concrete grade FCK is 30. The reinforcement FYK, reinforcement grade FYK is 500. So basically, and I've given you the links. Okay, the links have been provided. So the task that you have to do is check whether the links that have been provided is enough or not. That's basically what you have to do. Okay, so they provided the shear links already. You just have to check whether it's enough or not. Okay, so to do that, first of all, you need to know the shear. You need to know what shear force you are dealing with. Okay, they've given you a load, but they haven't given you a shear force. Okay, they've given you a load, they haven't given you a shear force. So you need to calculate the shear force itself. Okay, so what we did last week, we calculated the shear force. We calculated the shear force, and we think it looks like this. Okay, we calculate the shear force. It looks something like this. There. Okay, let me draw next to it. Wait, okay. Okay, there. Okay, let me go through this very quickly with you. Okay, very quickly with you. So basically, we have a beam, 8 meters long, carrying a UDL of 200 kilonewton per meter. Okay, so this is from the question. This is from the question. So I want you to check whether the shear links provided is enough or not. So you have to cut first. To do that, you have to first calculate the shear load, the shear force. So to calculate the shear force, you have to draw the shear force diagram. Okay, so how do you draw the shear force diagram? Well, first, if you go back to your theory of structures, you have to calculate the reaction. VA and VB. Okay, calculate reactions VA and VB. Wait, let me do it up here. Wait. Okay, VA. Okay, so you have to calculate reactions VA and VB. Okay, assuming this is A, this is B. Okay, so how do you calculate VA, VB? Well, theory of structures. So you have to go back to your theory of structures then. Simply supported beam with a UDL. VA would be the UDL times the span divided by 2, because half. So so basically what you have to do is you calculate the total load. The total load is 200 times 8 lah. Yeah, 200 times 8 gives you the total load. Once you have the total load, half goes to A, half goes to B, which is why you divide by 2. Okay, which is why you get 800. Yeah, 800 both sides. Yeah. Okay, so these are your support reactions. From your support reactions, then you can draw your SFD. Okay, from here you can draw your SFD. How do you draw your SFD? Well, you know at VA you have a support reaction of 800, so you draw 800 first. Okay, you start with a shear force. Sorry, you start with a support reaction 800. Okay, now what happens to the shear force diagram next? Okay, we know that along the beam you're gonna have a UDL of 200. So basically there's a UDL of 200 pushing down. Okay, 200 per meter. 200 kilonewton per meter run UDL. What that means is every meter you go, setiap meter, every meter you go towards the right, you lose 200 kilonewton. Yeah, because it's pushing down. So as you go 1 meter, you lose 200. So it becomes 600. And then another meter, you lose another 200, so it becomes 400. So eventually it's going to do that. Okay, eventually it's going to do that. Although it's supposed to be equal. 100 this. Roughly like that. Okay, yeah. So that's your shear force diagram. That's a shear force diagram. Okay, now, however, this shear force of 800 is at the support. Yeah, at the support. At the support. Okay. Our support is actually 300 millimeter wide. So zoom in. Our support is actually 300 mm wide. 300 mm wide. Okay. So you have to calculate the shear at the face of the support. So at the face, that means 150 lah, yeah, because 300 is in the middle. So 150. Okay, so that is called VEF, the shear force at the face of support. Okay, so we know the support is 150 millimeter away from the center of the support. So the UDL will have to reduce by a certain amount. So how much will it reduce? Well, I've done the calculation with you. There, VEF. Yeah, there. Yeah, you have to account that it's moved by 150. Okay, so VEF is actually 700 we calculated earlier. If you forgot, you go back to this calculation, you try to understand this calculation from last week. Okay, next, there is another calculation, another shear force that is important, which is at a distance D from support, which is VED. So VED we calculated is 640. Okay. So VED we calculated is 640. So VED is at a distance D from the face of support. Okay. So now we have these two forces. We can start doing our shear check. Okay. We check whether the reinforcement, the shear links provided is sufficient or not. Okay, basically. Okay. So the first thing you have to do is, now, I explained earlier, okay, last week, that the way a beam resists shear in Eurocode is they assume this truss, okay, strut and tie analogy. In other words, it behaves like a truss lah. Okay, it assumes your beam behaves like a truss. Okay, it assumes your beam behaves like a truss. Okay, so first, what you're gonna have to do is, okay, you have to check, you have to assume the angle of the truss. So this is our beam. This is our beam. Okay, so we assume the beam behaves like a truss. So like this. Okay, so this is your strut. This is your tie. Hence the system is called the strut and tie theory. Okay, the system is called strut and tie theory. Okay, so the first check you have to do is you have to check. Now, sorry, back to this again. So the strut and tie theory, obviously, you have a strut and you have your tie. Now, between the strut and the tie, there's an angle. This angle, there's an angle theta. Now, exactly what that angle is, no one knows. Yeah, we know there's an angle between your strut and your tie. Exactly what that angle is, we have to guess. We have to start with a guess. Okay. Now this angle varies between 22 degrees, paling minimum. So minimum, it can be 22 degrees. Maximum, it can be up to 45 degrees. Okay. So this angle can vary between these two values. Okay. But we don't know. We don't know which one it belongs to. Yeah. It depends. It depends on the loading and the beam size of and the dimensions of the beam. Okay. So we have to do a bit of trial and error. Okay. We have to do a bit of trial and error. Okay. So first thing first, we have to check the crushing strength V VRD max of the diagonal strut at face of support. Okay, so basically what that means is you have all your load coming down on the beam. That load will travel down the strut to get to so that it can reach the support here. Okay, so we want to check the strut at that point, whether it's going to crush or not due to shear. Okay, due to your vertical loads. Okay. Now, to calculate the force in that strut, we need to know the angle. So we have to start somewhere. So let's assume we start with the minimum first. So we try. Okay. We try the minimum 22 degrees. Okay. We try the minimum 22 degrees. And then we calculate VRD max based on that. Okay. So I'm gonna write VRD max 22 to denote that it's the VRD max for when I assume theta is 22. Okay. So VRD max, did I go through the formula with you? I think I did. Okay. So the formula is 0.124. Okay. This W is not it's a subscript. BW D 1 minus FCK divided by 250 times FCK. Okay. Okay. So let's try the calculation. 0.124. Now BW is the width of the beam. The minimum width of the beam. So in this case, we have a rectangular beam. So BW is B lah, 350. For this, always work in Newton and millimeter only. Okay, always work within Newton and millimeter only. Okay. Now D, what is D? D is 650. Okay, and then 1 minus FCK. FCK is 30 divided by 250. And then the whole thing you multiply by 30. Okay. So someone do this for me. Quick. Calculate for me. What's my calculator? Quick, someone. So 30 divided by 250. minus 1, 0.88. 0.8 times 30 times 650, times 650 times 350 times 0.124. What did you get?
248. 284.
284?
Is it? Oh, it's 315. Okay, 315.
350. 350 times 650. Yeah. Times this times 30 times 0.124. Yeah. Now, the unit. So VRD max. So VRD is shear. So V is shear. That means it's a force. That means the unit is either Newton or kilonewton. Okay. In this case, because we are working with that, this is Newton per mm square. This is also Newton per mm square. Therefore, your result will be Newton. Okay. So calculate for me. What is the force in Newton? Quick. Someone. Quick, someone.
Is it 1,000 plus?
1,000? Okay. No. Okay. Okay. Work with me here. Okay. Normally, what I do is, I'm gonna use blue color here. I'm gonna do this one first. Okay. Do that one. Let's do one by one. What is that? 1 minus 30 divided by 250.
0.88.
Correct. 0.88. Okay. 0.88 times 30.
26.4.
Okay. 26.4. Okay. And then times, okay, we've done this. Okay. And then times 350 times 350 times 650. How much? 600,6000. Agree?
Agree.
Yes.
Okay. Okay. Last times 0.124. How much?
744.
Yeah, correct. Now, obviously, this is Newton. Yeah, because the FCK is in Newton per millimeter square. Okay, so if you convert to kilonewton, then it's 745 lah. We round. Okay, 745. Now, 745. Is it bigger or smaller than VEF? VEF, how much? VF, we calculated earlier how much? 7? Yeah, 770, not 700, 770. Okay, we calculated VF here. VF, 770. Okay, so VF is 770. Our capacity is 745. Okay, so obviously it's less. Okay, so it doesn't work. Okay, so our concrete strut fails. Yeah, because our concrete strut, we only have a strength of 745. The actual force it has to resist is 770. Not enough. So let's try let's try the other angle, the bigger one, 45. Okay, let's try 45. So what I did is I tried the smallest angle, and then I tried the biggest angle, and then I get the two different strengths. Okay. So when it's 45 degrees, okay, so when it's 45 degrees, the formula is 0.18 BWD 1 minus FCK 250 times FCK. Okay, so you can see, when the, I want to point this out. I use green color. Okay, now you can see, green color not clear. Okay, blue. I use blue again. Now, pay attention. When you try an angle of 22 degrees, the formula for VRD max has 0.124 in front. The rest is the same. When you try 45 degrees, then it's 0.18. The rest is the same. Okay? The only difference between the two angles is that first number in front of the formula. Okay, pay attention to this. Yeah. Okay, so the rest is the same. So you take 745 divide by 0.124 times 0.18. What do you get? 1081. Now 1081 is bigger than VF because VF is 770 only. Okay, so now you know your VF, which is 7, is less than VRD max 45, but it's bigger than VRD max 22. Okay, so it's somewhere in between. So what that means is, this is assuming 22 degrees. This is assuming 45 degrees. Okay, so it's somewhere in between. So what that means is theta is somewhere in between 22 and 45. So you need to find the actual theta. Okay. So find actual. You need to calculate the actual theta. Yeah. Okay. Now the formula for theta is this. Zero 0.5 times inverse of sine VEF divided by your VRD max 45. Okay, so semua ada sudah, ya. So 0.5 sine in inverse sine VF is what? Well, 770. VRD max is what? 1081. That's it. Yeah, that's it. You just substitute the numbers in. VF, VRD max 45 degrees. Substitute it in. And then do the inverse side and then divide by 2 or times 0.5. What do you get? Do it for me, please. How much?
22.71.
Yeah, correct. You get 22.71 degrees. Okay, so that's the actual angle. So it's just a little bit more than VRD max 22. Yeah, 22.71. So it's 0.71 degrees more only than the minimum angle allowed. Okay, okay. So now that we know this, okay, we can actually proceed to check the resistance of the links. Okay. Okay, so to get the resistance of the links, we need to know the actual area. Okay, so what's the best way to show this? Okay, I have to do this in 3D. All right, I have to do this in 3D. All right, this is your beam. I'm trying to draw the beam in 3D. Yeah, so you try to keep up. My drawing is not the best. This is your beam. I draw half. I draw partial part of the beam. Okay. Right. Okay. So in the question, this is from the question. I didn't calculate any of this. So the question says the links. I need a thicker one. How do I get a thicker? Not thicker one. Yeah. Okay. So the question says the links. The links which start here. Yeah. So basically the links look like this in 3D. They are basically like square steel bars lah. Okay, yeah. And they just keep going. They just keep going. Okay, so the links are basically a series of steel bars. Steel bars in square. Steel bars bend so that they become square. Okay, that's how they arrange. Okay, so what they're saying is these steel bars, it's H12, meaning 12 mm diameter bars. Yeah, the H12 means 12 millimeter diameter bars, and at 175 centers or spacing. Okay. This is from the question. I didn't create this. This is from the question. Okay. So basically, it's a series of 12 millimeter diameter steel bars bent into rectangle shape. Okay. And you place them at 175 millimeter apart. Okay. So they are 175 millimeter apart. Okay. So every 175 millimeter, there is a rectangle shear links like this. Okay, so these things are called shear links to prevent shear failure, lah. Or some people call it shear reinforcement. Okay. Okay, so this is given by the question. So now, to continue answering the question, you have to know the area. You need to know the area of this shear link. Okay. Now, the ones that actually contribute is actually only the vertical ones. This one and that one. Okay, those two. Okay, so when we say we calculate area, okay, what you're actually calculating is the area of those two bars, the vertical bars. Okay, area of the vertical bars. Okay, so basically we have links like this. We need to know the area of that bar. We need to know the area of that bar. But they are both the same size. They are both 2 millimeter. So meaning they are both the same lah. A1 is equals to A2. Okay. Yeah, they are both the same. Okay. So total area of links is A1 plus A2. Okay. So we know the links H12, meaning the steel bar is 12 millimeter in diameter. What is the area? Calculate the area. Circle. Area of circle with a diameter of 12 millimeter. What is the area? Calculate for me. Pi R. What is area of circle? Pi R, pi D. You can do pi R or pi D. In this case, it's D lah. So you just use D lah. What is area of circle? Pi.
Pi r square.
Can I use D? Can I use D kah? Okay, never mind. We use pi R squared. Pi R squared. What is pi R squared? Calculate it for me quickly. Quick, how much? Someone else? Maybe from a lady this time. I want to hear.
1
Thank you. 1
113.0
Okay.
point 1.
Okay. 113 lah. Let's say 113. Okay, thank you. Okay. So area of a 12 millimeter bar is 113. So that means A1 is 113. A2 is 113. Okay. So what that means is A1 is 113, A2 is 113. So total area is 113 plus 113 lah. Which is what? 226. Okay, 226. All right. So shear resistance, the formula, shear resistance VRDS provided by the links. So this is called links lah, the steel, okay, is Is this formula? Okay. ASW. So let me do the links. Let me do the linking here. ASW is area of links. Okay. ASW is area of links. S is the spacing. Spacing. S is the spacing. Okay. D, you know lah. D is in the question. Yeah, D is the design depth of the beam. Yeah, the 650 tadi. FYK also given. So this is given in question. 650. This is also given in a question. Theta. Theta is the 22 we calculated just now. 22.71 we calculated just now. So I've joined everything out for you. Now you calculate for me. What is VRDS? So ASW is what? ASW 226. Spacing is 175 times 0.78 times D 1650. FYK 500 times cot 22.71 degrees. Okay, I put everything in. How much? I got 781 kilonewton. Okay, I got 781 kilonewton. Okay. So for this one, you need to check against. So this is your strength, your beams, your reinforcement strength. So now you have to check against the load. So you have to check against the load, which is VED. VED. VED is the shear force at a distance D from the support. We calculated that earlier. VED. There. 640. VED. 640. Okay. 640. Okay. So our shear link has a resistance of 781. The shear force at D is only 640. Does it work or not? What I provided? Yes or no? This 640 is what we have to carry. 781 is actually what we have. Is the strength. So meaning this is what you need to carry. This is what you can carry. Okay? VED is what you need to carry. VRDS is what you can carry. So you need to carry 640 and you are strong enough to carry 781. Can you carry the 640 or not? Can you carry the thing?
Yes.
Yes. Yeah, you can carry the thing. Means the beam works lah. Okay. So it means the shear links can carry the design shear force. Okay. That's your answer. This is your answer. Shear links can carry the design shear force. Okay. Okay. So generally there are two checks we do. The first check is the crushing to get the angle theta, and then we do the actual shear link check. Okay, to see whether the shear link can carry the load or not. Okay. Now there's a last part of this. Now let me draw the beam again. That's your beam. That's the strike and tie. So we calculated the force here. We checked the crushing at the end, but we haven't calculated anything for the tie. We need to know what is that tie force as well, because that tie force is tension, and it will put additional tensile forces at the bottom of the beam. Yeah, bottom of the beam is bending, it's undergoing tension sudah. Now we are, because of this strike and tie model, we are putting additional tension in that bottom of the beam. So we need to check whether how much we have to increase the reinforcement by. Okay, so we also need to calculate additional tensile force in tension steel. Okay, we also need to calculate the additional tensile force in the tension steel at the tie location. Okay. Okay, so to calculate the tensile force, again, you need to know the angle theta, which we calculated already. So no problem there. Okay. So no problem there. So the formula is delta FTD. So this is the additional tensile force, and it's 0.5 VED cot theta. So 0.5 VED, we know VED we calculated earlier. VED is the force at the distance d. Where? VED is 640 times cot theta is 22.71. Okay, what is that force? It's 765 kilonewton. Okay, so normally when I give you a question related to links, it will be something like this. Okay, it will be something like this. You have to do a check. I will give you the links, amount of links, and then you have to check to see whether the links work or not, the links provided, whether they work or not, and you also have to calculate what is the additional tensile force due to the strike and tie model. Okay, at the bottom of the beam. Okay. So shear flange, we don't care. Anchorage, we don't care. Okay. Next week, we're going to do span depth ratio. And then we are going to go into column design. Remind me quickly, what week are we in now? What week are we in? I forgot. Kita week berapa sudah sekarang?
7.
Oh, week 7 lah. So next week is week 8 lah.
Yes.
Okay, thank you. Okay, so we are halfway there. Okay, no problem. So next week, we do span and depth ratio quickly, and then we do the column design. And then, no, let's do slab first. Okay, we do span depth ratio, and then we do slab design, and then we do column design. Okay, yeah. Okay, now, next week, convo kan? Is next week the convo thing?
No, no.
Not next week. Okay. Let me get my calendar. Today's the 21st. When's the convo? Huh? I remember getting an email saying I have to ask you something. I have to ask you guys something. I have to offer you online classes next week. Is it next week or week after? Okay, never mind. Let me check and then I will ask you next week. Okay. I will ask you next week. Okay. Now, before we end the class, how are you getting on with the assignment? So let me guide you quickly. So for the assignment, you assuming you obtain the architectural plan. Let's say architectural plan looks like this. Yeah. What does the building look like? Okay. You have ground floor. You have first floor. Okay. I'm on 2-story, so there's a ground and first floor. Okay. So let's say the building plan that you obtained looks like. Let me think. Okay, looks like this. This is your backyard toilet. This is the kitchen wall. This is the wall between you and your neighbor. This is also a wall between you and your neighbor. And then this is your front porch. And then you have the porch roof. Okay, let's say the first floor looks like this. All right. And then the ground floor. No, maybe first floor we don't have this. Wait, we make it a bit special. This is the neighbor wall. And like this, first floor does that. Okay, ground floor, you have your ground floor toilet here. And then it does this. Okay, so the two obviously don't quite line up. Okay, ground floor, you have the extra at the back. Okay, so this is front. So this is front of the house. This is the back of the house. Okay. So let's say this is your structure. All right. Now, what you have to do then is you have to put in the slab, the beam, and the columns. Okay. So as I explained last week, the beams support the slab. Yeah. The slab is what you stand on. Yeah. The slab is what supports you. Let me write it here. Okay. Slab support the loading directly lah. You can say directly. Yeah. In a normal building, slab supports the loading. Then the beam support the slab. Then the column support the beam. This is the hierarchy. Then the foundation support the column. This is the hierarchy. This is how the load travels. Okay, this is how the load travels. The load travels to the beam. No, sorry, to the slab. The load goes onto the slab. And then the slab is supported by the beam. The beam is supported by the column is supported by the foundation. Okay, this is the hierarchy, the normal hierarchy. It's not always like this. It's not always like this, but normally it's like this. Okay, normally in a normal building it's like this. Okay, but there are some structures which doesn't follow this rule lah. Okay, but we don't worry about that. Okay, so this is hierarchy. So there's interconnecting forces here. All right, so you need where do you start? Okay, so normally we start from the highest up floor. Okay, because you obviously actually also have a roof, but you also have a roof. So maybe your roof does that. Okay, you also have a roof. Okay. So normally what we do is sorry, for each floor, we need to show the beam and the columns and the slab. Okay. Now roof in the and then when we frame up the building, okay, when we frame a building, we start from the highest floor. We start from the highest floor. Okay. In this case, the roof. Okay. Now roof, because you already have a roof, you don't need a slab. Okay, because you have the roof covering, you have the roof to carry the roof load. So you don't need a slab. So you only need beams. So the roof sits on the beam in this case. Okay. So then so on your architectural plan, so on your architectural plan, you have to start showing where your beams and where your column goes. Okay. So if it's a rectangular roof like this, so you start from the highest up. So we start from the roof. So if your roof is a rectangular roof like this, okay, normally you put column in each corner. You start from each corner. Okay. One column in each corner. Now, when I show columns, I always show column below. It's always column below, not column above. We don't care about column above. We only care about column below. Okay. Okay. So when we show columns, we show column below. When we show beams, it's beam at that level. At that level. Okay. Now the next thing you have to do is, okay, we have columns. The columns need to support the beam. Okay. So you can start putting beams between the column. Okay, you start showing your beams. Okay? So these are your beams. Beam. Okay, so you take the architectural plan, you take a marker and you mark like this. Okay, where the column go, where the beam goes. Okay, now at some point you will realize this beam. Let me get another marker. Let me get another color. Bear with me. Okay. This beam in red looks a bit long. This beam in red looks a bit wrong. So next week I'm going to teach you. How do you decide whether something is too long or not? Okay. Next week I'll teach you. How do you decide, is that beam too long or not? Okay. There is a way you can check very quickly. Okay. There is a way. We call it a span deck. Is this beam too long? If it's too long, if it's too long, the solution is we put a column in the middle. Okay, put column in the middle, or we can put two. We can put three. Okay, but you need to decide if it's too long or not. If it's not too long, then you don't have to put any columns in. If the beam is too long, then only you have to put columns in to put more supports lah. The more column you put in means there are more supports supporting that beam. Okay. Then it becomes shorter lah. Okay. So how do you decide whether you need to put additional columns in or not? So this is obviously a question of, it comes down to a bit of experience as well lah. Okay. So is this beam too long? The way we decide is for beams and slabs, we can do this thing called span depth ratio check. It's a very quick check that you can use to decide whether your beam and slab is too long or not. Okay. Next week, I will teach you how to do this. Okay. Okay. So now, let's say we put 6 columns in. So now we go down to the floor below. We have to continue the columns below. If you have 6 columns above, you have to make sure you also have your 6 columns below. The columns cannot stop halfway. The columns cannot stop halfway down the building. If you have 6 columns above, you have to have 6 columns below. Yeah? Yeah. Okay, one here, one here. So basically what I do is I copy the columns from floor above to floor below. Okay. Now, first floor, you have a slab because first floor is a floor. So you have slab. Okay. So maybe I put beams in for the first floor. And then I can put the slab. So the way you show slab is you show the span of the slab. So if I put arrow like that, that means my slab is spanning between the beam on top and the beam below. Okay. And then the side beams are not doing much. They are just restraining the columns. Okay. Okay. Now, then you copy the column to the floor below. Again. Again. Okay. Then you can do the same thing. And then you show the steps when. Okay, that's it. Okay. So now you have, this is what we call framing a building. Now our building has a frame already. Okay. You can actually start designing the beam, slab, and column. Okay, if you know how lah. Okay. Now, sometimes there is a problem. Sometimes there is a small problem. Okay. Sometimes there is a small problem. Now, on the ground floor, we have this little area at the back. This little area at the back, which doesn't exist above. It only exists on the ground floor. So you have structure there. So you have to provide beam and column for it as well. Okay. Okay. Oh, that thing will also need a roof. It also needs a roof. This is a roof. So you also need it here to support the roof. Okay, now I finished framing it. Now, sometimes there is an issue. Ground floor, you notice something. This column is like in the middle of an area. I may want to park my big Hilux there. That's my Hilux. I want to park my Hilux there. That column will be in the way. Architect will say, I don't want a column there. Move that column away. Okay? Yeah? So sometimes you have this issue. You put a column there, it's a logical place. But that column is only logical for the floor above. Yeah? Here. In the roof, it's logical. First floor, still okay. Maybe still okay. But ground floor, if you put a column there, it's in the middle of the porch. If I want to park my Fortuner there, it gets in the way. So what happens then? So now you have to start playing around. You may think that maybe I cannot put a column there. I have to put a column somewhere else. Yeah. So there are issues like this. I let you think how you're gonna solve this. Okay. This is like a puzzle for you. You think how you're gonna solve this. So you follow my principle. You follow my principle. You do this for your building first. Okay, for your chosen building. Okay. You do this for your chosen building. Put the columns and the beams and show the slab span direction first, and then we go from there. All right. Now, does everyone have a group already?
Yes.
Okay. If you don't have a group, you PM me later. Okay. I'll try to find a group for you. Okay. Try to fit yourself into group. Try to fit yourself in the group. You have to start looking at this now. Okay. So you have to be inside a group already. Okay. Okay. That's it for today. Don't leave. Attendance first. Okay. Several participants have left. Wow, who left already? It's okay. They won't get to do the attendance then. Attendance. Okay. Belum habis kelas pun cabut sudah. Apa ni? You want go dating, you have Saturday and Sunday mah. Hey, connection closed. What's wrong with you? Force design, correct. Wait, something wrong with the system. Parsec error. Alamak. Okay. Okay. Get ready to scan. All right. Okay. Those of you who have done the attendance, you feel free to leave. Okay. I will see you next week.
Thank you,
Thank you,
Doctor.
Doctor.
All right.
Thank you, Doctor.
All right.
Thank you, Doctor.